Okay, people, we should get into this. So, housekeeping stuff. There's a bit of stuff today. So, remember, quiz 2 is due Wednesday next week. Next week, we're going to miss our Friday seminar because of the holiday. So instead, I will just do up a recording of that and put it straight on Echo. So you can watch that anytime from when it goes up until our first seminar back, right? If you'll miss your applied class because of the Friday holiday, you'll get participation credit automatically, but we'll also put on a bunch of online makeup classes during the week next week. I think we're in the process of sorting that out, but I think there'll be one each Tuesday, Wednesday, Thursday. Details will go up on Moodle over the weekend. Assignment 2 comes out tonight, but it's not due for a good while. It's only due after the break. Solutions to assignment 1 will be up late next Tuesday. Normally that's Monday, but because the due date was a day late, I thought we'd delay the solutions a day too. Okay, so we're going to finish off talking about sets today, and we're going to talk about operations we can do with sets. So let's get into it. Yeah.
On the calendar it says that Monday is the workshop replacement, lecture replacement, sorry, but you said it's
On the calendar it says Monday is
7 p.m. to 8 p.m. online as a replacement for Good Friday.
I don't know anything about that.
It says, yeah, match 18:30, seminar online 7 p.m.
Okay, I'll talk with you about it afterwards, but I don't know anything about that, so I would ignore it. Yeah, I don't know what the story is with that, sorry. I'll have to investigate. Okay, so we're talking about operations on sets. So, we'll be using a bit through this seminar the idea of Venn diagrams. Hopefully that's an idea that's familiar to people, the idea, of course, is we have some universal set U, some set of things we're interested in, so maybe it's all the integers, for example. We imagine them scattered around in this big rectangle that represents U, and then we have circles within that rectangle that represent various subsets of U. Right, so A might, for example, represent all the positive integers or all the prime integers or something like that. So that's the idea. So let's get into it. So our first operation on sets is the union, right? So the union of two sets is the set of all things that is in, so the union of A and B is the set of all things that are in A or in B. Right, so it's tempting to think this is sort of an and because it feels like putting them together, but the better way to think about it is that this is an or, right? You get into the union by being in one set or the other set. So the bouncer on the door of the A Union B club accepts membership cards for either Club A or Club B, right? You just have to show one of them and you're let in. So that's the union. Intersection is the proper and, right? So to get into the intersection, you need to be in A and in B. So it's just this overlap here, right? So the bouncer on the door of the intersection club, you need to show both your membership card for Club A and your membership card for Club B to be let in. Make sense? Okay. So, in that case, let's do some questions. So what are some things in this union? Name me some of them. 1, 2, 3, 5, and 7. So all the stuff, right? But notice, of course, that 2 is not in here twice or anything because you only go into a set once, right? You're either in a set or you're not in the set. There's no notion of multiplicity. So good. Okay, so what if we take the intersection instead? What's the intersection got in it? Just 2 and 3, right? So just the things that are in both of those. What's this? Just the set containing 1, 2, and 3, because if I take a union of any set with a subset of that set, I'm just going to get the set back, right? Taking a union with a subset doesn't change things. What about this? Just the set containing 3. How about this? Empty set, right? There's nothing which is in both of these sets. So good, good. Any questions on that? Okay. So, next thing then is set difference. So this can be a little bit weird. So you also sometimes see this represented with a slash. So just be aware of that, a down slash. Okay, so the difference, A minus B, is all the stuff that is in A but not in B. So there's a couple of things to note here. I guess the most important one is sort of, there's all this stuff in B here that doesn't really matter, right? Because of course you can't be in a set a negative number of times either, right? So it would be just the same if we only subtracted from A intersection B, right? That would make no difference, same deal. So A minus B, you just look in A and then you throw away everything that's also in B. So the bouncer on the door of the A minus B club, you show them your A membership card and then they frisk you to check you don't have a B membership card as well, right? You need to, or they look up their list of everything in B and check you're not on that list, right? So you need to be in A, but not in B, right? And there's a special sort of set difference which we call the complement, right? So if we know that we are working in some universal set and we need to know what that set is before defining a complement, but if we know we're working in the integers, say, then the universal set, the integers minus B, is called the complement of B. So for example, if U is the integers and B is the positive integers, then the complement of the positive integers is the negative integers and 0, right? And sometimes we represent a complement with a line over the top of something. So the complement of B in this Venn diagram is everything that is not in B. Make sense? Awesome. So, the last of these that we'll deal with, well, in this first little section is the symmetric difference. So, written with this triangle, and to be in the symmetric difference, you need to be in one but not both. So which logical operation does this correspond to? It's an exclusive or, right? You need to be in one but not both. Yes, yep. So you can think of this in a couple of ways. One is to think of it as being the union of this sort of crescent here, which is of course A minus B, and this crescent here, which is B minus A. You can write it like this. But of course you can also think of it as taking everything which is in the union, everything which is in both these blobs, including this, and then subtracting away the intersection. Right? That gives you these two things, but minus this middle piece. So a couple of different ways of getting the same result, getting this symmetric difference. So, okay, what is this going to be? Yeah, so I think it's got, we remember, we only have to look at what's in here and then throw away anything that's in here. So I think we're going to wind up with 1 and 3 in this set. And notice that the 5 and the 7 were sort of not important here, right? You know, as I said, you can't be in a set a negative number of times. So they were irrelevant. It would have been just the same to subtract just the set containing 2. How about this? To get into the symmetric difference, I need to be in one but not the other. So I think I get 1. I don't get 2 or 3 because they're in both, and I get 6 and 7. Make sense? How about this? That's our friend the empty set, because 2 and 3, but then I throw away everything that's in here. That includes 2 and 3, so nothing left. How about this? Just the set containing 1 and 2, because 3 doesn't get in because it's in both, right? Make sense to everyone? Any questions about this? How about this?
1, 2, 3.
Just 1, 2, 3, right? If you subtract a disjoint set from a set, you're doing nothing, right? Disjoint's a fancy way of saying they don't have any intersection, right? The two circles are completely disjoint. Okay, so I've done the easy questions. I'm going to give you a harder one. So have a bit of a talk about this and see what you think. How are we going? Another 30 seconds or so. Okay. So I think I do agree with the majority of you here, but let's go through it. So, firstly, what is S here? So S is everything that is in both this set and in N, right? So it's just 0, 1 and 2, right? Remember our naturals include 0, so this is S. Now, if we know that S is a subset of this stuff, union T, then we need, by the definition of subset, that each thing in S is in this set here, right? Now 0 is definitely in this set here because if it's in this set, it's in the union. And 1 is definitely in this set here because if it's in this set, it's in the union. The question is 2 in this set here? Well, 2 will be in this set here. I've got an extra comma there, I apologise. 2 will be in this set here exactly if 2 is in T, right? And so definitely true for 0 and 1 because they're in this. We just need that 2 is an element of T. So that's the condition we need. Anything that 2 is an element of T will satisfy that. Any questions on that? Yeah.
Well, I know that we just need 2 to be an element of T.
Uh-huh.
I also think, why not T must equal N? Doesn't that
What-
work as well?
T equals N does work. I would object to the must, right? I mean, I've phrased the question fairly informally, but I say, what can we say about T, right? Now, to my mind, can we say that T must equal N? No, we can say it might equal the natural numbers, but it could equal lots of other things as well. So this would definitely work, but to say, or indeed this would definitely work, right? A would definitely work as well, but it could be lots of other things as well. So I don't like those answers because they say it must equal that thing, rather than if it was could, I'd agree. Does that make sense?
Yeah.
Yep, cool. Okay, God. Okay, so here we are. All right, so question 12.1 in the notes wants us to draw a Venn diagram for A intersect B complement. What's another name for this set? So you can sort of build up Venn diagrams in the same way you can build up truth tables, right? So here's a Venn diagram for A. Here's the Venn diagram for B complement. I apologise for the light yellow colour. Now, to get the Venn diagram for A intersect B complement, we need the stuff that is shaded both here and here. The stuff that's shaded in both is just this crescent, A intersect B complement. What's another name for that? A minus B. So A minus B is just A intersect B complement. What would this be in logic then? I need to be in A and not in B. right? So it's a sort of an and not situation. Okay, so let's sort of recap the connection between the set operations we've seen and logic. So X is in A union B if and only if X is in A or X is in B. Good. So we can even use our logic notation if we like. X is in A or X is in B. In the intersection, if and only if what goes here, and absolutely. A minus B, what did we just say? So X is in A and X is not in B. Or you could write not X is in B if you'd prefer, whatever you like. This one, what did we say before? That's XOR, right? So X is in A, exclusive OR, X is in B. All make sense? Okay, so question 12.2 asks us to show this is true using Venn diagrams. What logic law does this remind you of? Absolutely, this is a De Morgan's law type situation, right? We're sort of saying complement, which is kind of like not, of a union, which is kind of like or, is the intersection, which is kind of like the and of the complements, of the nots, right? So this is what A union B looks like. This is what A union B complement looks like. We shade everything that was not shaded in the original diagram. This is A complement. This is B complement. So to get A complement intersect B complement, we shade anything that was shaded in both of these. That's just this outside bit, and you can see we've got the same diagram here, right? So that's the truth. For any sets A and B, this will hold. Okay, the other way around, I'll be a bit quicker. A intersect B looks like this. Unshade or reverse the shading to get A intersect B complement. Here's A complement as a Venn diagram. Here's B complement. Union, shade anything that's shaded in here or in here. That's all of this, right? So that's the other De Morgan law. Okay, so how would we show that this is the case using logic? Well, we could use exactly what we just talked about, right? So X being, so remember that two sets are equal exactly if they have the same elements. Or in other words, two sets are equal if being in one is logically equivalent to being in the other, right? So that's what we're going to try and show. So being in this left-hand set, X in here, is, well, logically equivalent to not being in the union, right? Because to be in a complement, you have to just not be in the original set, right? Now, to be in the union, well, that's logically equivalent to being in A or in B, right? So this is logically equivalent to X in A or X in B. And now we said that the set thing was kind of like De Morgan's law. Now we can actually use proper De Morgan's law here, right? So use De Morgan's law here, and we get not X is in A and not X is in B. And then being not in A is the same as being in A complement. Being not in B is the same as being in B complement. Being in A complement and in B complement is the same as being in A complement intersect B complement. Right, so we're just sort of translating the set stuff into logic stuff using De Morgan's law and then untranslating, right? Translating back to set stuff. Does that make sense? Okay. horribly dated these days. We need Spotify Shuffle or something in place of Pandora. Okay. So, little bit more practice with more complicated Venn diagrams. So obviously we can do these for 3 sets too. Remember, a very long time ago, we had questions in the logic section about whether AND distributed over exclusive OR and vice versa. This is the set version of those. So, okay, anyhow, a bit of Venn diagram practice. Here's A in our 3-set Venn diagram. This is B symmetric difference C, these sort of bat wings here. And when we take the intersection, what is shaded in both of those? Just these 2 triangles here. And the other side of this, well, here's A intersect B in our 3-way Venn diagram. Here is A intersect C. Symmetric difference. It's what's in one but not both. It's just this thing. Same deal, right? So this one does work. If we tried this the other way around, though, we'd, I think, run into problems. So question 12.3 asks, the second part asks this the other way around. Here's A, here's B intersect C. Symmetric difference, well, things that are shaded in one of these but not both, we wind up with this. Whereas if we take asymmetric difference B and asymmetric difference C, they look like these 2 things. And then intersection, we are just looking at the things that are shaded in both. And it's just this and this, which is different from these 2. So I guess to answer the question properly, is this the case? The answer is not always, right? Of course, for some sets, it might be the case that these are equal, but in general, they are not equal, right? So some choices of A, B, and C, it would be equal, but in general, not the case. That makes sense as well. This one I think is not dated, still as true as ever. Okay. So, good. So that was the first bit of this lecture. That was our sort of basic set operations, right? Now, that I think mostly people get okay. This second bit of the lecture, try and wake yourselves up a bit because it gets a little bit trickier, or at least there's one point I'll be coming to that I think people get a bit confused on. Okay, so remember that for sets, we don't have any notion, any idea of order in them, right? It's just a bag, there's no order to the elements in the bag. But of course, sometimes we really want order. Sometimes that's important, right? You know, this is why programmers deal with arrays and mathematicians deal with sequences and lists and, you know, all sorts of things, right? So sometimes order is important. And we can define ordered pairs where the order is significant. So let's do that. So, and of course, if you're going as far as pairs, you don't have to stop there. You can do ordered triples, ordered 4 tuples, ordered however much you like. So, we can talk about ordered pairs, and notice now our definition of two things being the same has changed. Ordered pairs are equal exactly if their first coordinates are the same and their second coordinates are the same, right? So obviously as sets, the set containing 0 and 1 is the same as the set containing 1 and 0, but as ordered pairs, 0, 1 is definitely not equal to 1, 0, right? So a different object, a different data structure, if you like, however you want to think about it. Okay, so that's the critical property of ordered pairs, is that they're equal exactly if their first coordinates are equal and their second coordinates are equal. This is a tiny diversion, but just one I thought some people might find interesting. I mentioned in the last lecture that sometimes people build up basically all of maths from sets. There's sort of a question of, well, how could you possibly introduce order if your fundamental data structure is unordered? And the answer is actually it's not that difficult if you're a little bit cunning, right? One way is to define the ordered pair AB as a set that has firstly a pair set in it. So this, well, I shouldn't say firstly, it has a pair in it. This tells you that the two things in your ordered pair are going to be A and B. And then you put a singleton set in that set as well, which tells you what the first thing is, right? So, you know, if you want to do it, if you want to base everything on sets, you can, right? Not important really for us, but you know, I think a cute little example of how you can encode anything in sets if you want to. So the two element set tells us what the two things in the ordered pair are, but not their order. Then the one element set tells us which of those things comes first. Okay, so this is the thing that I said people get a bit confused by in terms of set operations. So the last important set operation we're going to learn here is the Cartesian product. And it's not like union or intersection or symmetric difference or the other ones we learned, in the sense that if you take a union of two sets of numbers, what you get back is a set of numbers, right? Same with symmetric difference and all that. In this case, whenever you take a Cartesian product, you get a set of ordered pairs, right? Ordered pairs of whatever was in the sets you took. So what's the actual definition? The ordered pair, the Cartesian product, A cross B, so we just use the times symbol where A and B are sets, is the set of all ordered pairs whose first coordinate comes from A and whose second coordinate comes from B. Right, so order is obviously important here. So the reason this is called a Cartesian product is if you say take all the real numbers cross the real numbers, then you get the set of all ordered pairs whose first coordinate is a real number and whose second coordinate is a real number. Of course, that is just the Cartesian plane, right? Or you can think of it as the Cartesian plane if you like, if you want to think of them as x and y coordinates, right? But we can do Cartesian products with any sets we like. So remember, elements of A cross B, sometimes rather than saying Cartesian product, people just say cross. The elements of A cross B are always ordered pairs. So name me some elements of A cross B here. Yeah.
0, 1, 0, 2, 0, 3.
Yep, so the ordered pairs 0, 1, 0, 2, 0, 3 and 1, 1, 1, 2, 1, 3. Totally agree. So here we have every ordered pair whose first coordinate comes from here and whose second coordinate comes from here. Is this making some sense? Good, good. Okay, and of course we can do this even if the sets are not finite. If A is 0, 1, what is A cross n? Well, I'm going to get all the ordered pairs which are 0 followed by any natural number, and all the ordered pairs which are 1 followed by any natural number. So I could write it like this, right? I get 0, 0 and 1, 0. I get 0, 1 and 1, 1. I get 0, 2 and 1, 2, and so on all the way up, right? Okay. How are we doing? Okay. Good stuff. So, negative 1, 1 is definitely in S because negative 1 is here and 1 is here. But 0, 1 is not going to be in S because we would need 0 to be in this first thing. So good, good. Okay. So, just to finish off, there's some sort of good reasons why we use a multiplication symbol here. So firstly, if A and B are finite, then Cartesian product A cross B has size of A times size of B elements in it, right? Sort of for obvious reasons, right? You need every ordered pair whose first thing comes from A and whose second thing comes from B. How many choices do you have for your first thing? Size of A. How many choices do you have for your second thing? Size of B. Well, then in total you're going to get size of A times size of B things, right? So that's one thing. And also you can sort of even think of that this works in slightly more continuous settings. If you think of L as being a line of length L and W as being a line of length W, then L times W, if you think of it in the Cartesian plane, is a rectangle with length L and width W, right? So again, there's sort of this multiplication-y thing going on. So there's sort of good reasons for using the multiplication symbol here, but the big important thing we need to remember is that if our sets are finite, the first one has this many and the second has this many elements, then our Cartesian product, to find the number of elements in that, we just multiply the two sizes, right? Okay, so just to finish off, these are very vague questions, but to play around with the concept of Cartesian product a bit, we sort of saw that if you took the whole real line and multiplied it by the whole real line, took a Cartesian product, then you got the Cartesian plane. What would we get if we multiplied a line and potentially infinite line by a particular circle? Any suggestions? Yeah, so the way to think about this is you're sort of more or less, you've got an axis and you're sort of running your circle along that axis, right? And it's going to trace out a whole cylinder, potentially, going, potentially if your line is infinite, going infinitely, if your line's finite, only going finitely. What would we get if we crossed a circle with a circle then? It's really tempting to say a sphere, but I don't think that's actually the best answer here. It does depend how you set things up. But if you imagine that I've got a circle around me, say, and then I've got another circle that I am running around that circle, then what I'm getting is basically a donut shape or a torus, right, is the fancy mathematical word for that. So, yeah, that's just hazy stuff, just for fun, but I think the right answer here is a donut rather than a sphere. So, that is all I've got for you people. I will see you Tuesday. Ignore this Monday night business. I'll say something about it in my end of week wrap up, but I don't know anything about it and I don't want to drag you here at 7 p.m. on a Monday.
It's not here, it's online.
It's on. That's even stupider. Okay. Yes.
I had a question. You said there will be makeup class.
Yes.
So is this only for people who will be missing the class because of the thing, or is it for anyone who's probably going to miss the class like in the previous weeks?
Basically it's intended for people who are missing their classes because of the Friday holiday. If you're really keen to get along to one, I'm happy for you to, but it doesn't give you back participation marks or anything like that. Thank you.
Just one question. So I understand this one, but if it was curly brackets and we said -1, one set belongs to S, then it would have been true?
So no, because if you have curly brackets,
That order doesn't really matter there.
yeah, but the Cartesian product is a set of ordered pairs, right? So it doesn't contain any sets at all, right? So like, yeah, like, you have 10. We've got this pen, low tech. So, like, if I write this out as a -1, 1 times 0, 1, 2, then that really is this set here. -1, 0, -1, 1, -1, 2. Sorry, I know you know this, but 1, 1, 1, 2. So, everything in here is an ordered pair, and an ordered pair is not a set, right? They're just different things, the way we think of them. So, anytime you ask, like, is xy in A times B as a set, the answer is no, because A times B just doesn't contain sets. Does that make sense?
Makes
Yeah,
sense.
yeah,
Thank
yeah.
you.
No worries.